In this module, we will discuss parallel reactions. In our exploration of chemical reactions, we have primarily focused on scenarios where a single reactant decays into one specific product. However, in many chemical processes, a single reactant has the potential to transform into a variety of products. These processes are known as parallel reactions. Parallel reactions involve multiple reaction pathways, each leading to a different product. This complexity is a common feature in many chemical systems, where a single set of reactants can yield various results. Let's consider a reaction mechanism where the reactant A can transform into one of two different products, P1 or P2. This mechanism is represented by the following reaction scheme. Reactant A can convert to product P1 with a rate constant K1. Alternatively, A can convert to product P2 with a rate constant K2. We consider the situation where both reactions are first order with respect to the reactant A. The differential rate expressions for the reactant A and the products P1 and P2 follow from this reaction scheme. For the reactant A, the rate of change in its concentration over time is the negative of the sum of its conversion rates to both products, represented by this equation. For each product P1 and P2, the rate of formation is directly proportional to the concentration of A and their respective rate constants. To integrate the differential expressions for the considered reaction mechanism, we further assume that only the reactant A is present in the system at the beginning of the reaction. The initial concentration of A is non-zero and the initial concentrations of the products are zero. Then we can obtain the time-dependent concentrations of A and the products. The concentration of A decreases exponentially over time as the initial concentration of A multiplied by exponent of the negative of the sum of rate constants K1 and K2 multiplied by the time t, and the concentration of each product P1 and P2 at any time t is given by the initial concentration of A multiplied by the ratio of respective rate constant to the sum of rate constants multiplied by 1 minus exponent of minus the sum of rate constants multiplied by t. These equations provide a quantitative description of how the concentrations of reactants and products change over time in a system undergoing parallel reactions. This figure illustrates the concentrations of the reactant and products in parallel reactions. Together with the underlying equations, it helps us understand some key characteristics of parallel reactions. First, we observe that the decay of the reactant A occurs with an apparent rate constant that is the sum of the rate constants for each parallel reaction. This combined rate constant governs the overall rate at which A is consumed in the reaction. Second, a notable feature of all parallel reactions is that the ratio of the concentrations of products P1 to P2 remains constant throughout the reaction and equal to the ratio of respective rate constants. This constant ratio of product concentrations, irrespective of time, emphasizes an important aspect of parallel reactions. The distribution of product concentrations is determined by the relative magnitude of rate constants of the parallel pathways and not by the duration of the reaction. We can easily generalize our discussion to parallel reactions producing any number of products. Consider a reaction where a single reactant A can form several products labeled as P1, P2, Pi, Pn, each with its own rate constant K1, K2, Ki, Kn. The differential rate expression for the decay of A and the formation of each product Pi is given by these expressions. For each product Pi, the formation rate is equal to the product of the rate constant Ki and the concentration of the reactant A. Upon integrating these expressions with the same initial conditions as before, we obtain the following equations. They reveal that the decay of A is governed by the sum of all rate constants, reflecting the cumulative effect of all parallel pathways. The concentration of each product Pi at any time t depends on its rate constant Ki and the sum of all rate constants. The ratio of concentrations for any two products, Pi and Pg, like in the case of two products, is independent of time and equal to the ratio of respective rate constants. In parallel reactions, the amount of product formed is linked to the rate constant of the corresponding reaction pathway. This relationship can be understood in terms of probability. The larger the rate constant for a specific reaction pathway, the higher the probability of the corresponding product being formed. This concept is quantified by the yield, denoted as phi, which represents the probability that a particular product will be formed from the decay of the reactant. The yield for each product is defined as the ratio of its rate constant Ki to the sum of the rate constants for all possible products. This formulation ensures that the total yield, which is the sum of the yields for all products, equals 1. This approach provides a clear and quantifiable way to predict product distribution in parallel reactions, emphasizing the role of kinetics in determining the outcome of such reactions.